So you guys have been working on a bunch of gravity stuff. We started with some things like falling and stuff like free fall, which is actually just an application of stuff that you guys have worked on before in terms of acceleration using DTV and VAT, except with the acceleration due to gravity. You got to look at the nature of gravity a little bit and that type of stuff. So you guys looked at some mechanical type stuff with gravity, applying the ideas that you guys took with basic kinematics to gravity, which is basic free fall. Well, now we're going to start looking at another aspect of gravity that we can do, which is also connected to some stuff that you guys have already done. And we are going to start looking at something that is actually called, statics, which is, before you guys looked at gravity stuff with things moving, and now you're going to look at things with gravity that are not moving. So we still have forces, but things are not moving. So we're basically in equilibrium, where the net force is always equal to zero. So things aren't moving, and this is often referred to as statics. Now, statics is actually a really, really common thing. It's actually all over the place. A lot of times when people start looking at statics and stuff like that, they start thinking about stuff like this. Things like bridges, structures like skyscrapers, just buildings in general, any kind of construction thing. There's a lot of statics involved, where we're looking at the forces and things like the cables and the supports and all that type of stuff. Because you can't just build a bridge and hopefully it works out. You got to analyze the force involved. They aren't really moving or going anywhere. You got to look at all the tensions and the stress and all the type of stuff in the actual structures themselves. Even natural stuff out there like spider webs and stuff like that, or trees, any type of natural structure. Some of them have just amazing tensions and forces they can withstand. Like spider webs, for their size, are absolutely amazing. And we can look at how the strains and the tensions and that type of stuff work. And we often like some things of spider webs, like the structures of spider webs and how the webs and stuff that are actually kind of similar to like cables and stuff and bridges and stuff that. So a lot of these things connect. Even other simple little things, like even just signs that you might see hanging on the side of a building. Even just simple stuff like that. Anything hanging, actually, hanging pictures, hanging signs, hanging a planter, hanging a lot of this has to do with statics and the tensions and the forces and all that type of stuff. And all these different things, they aren't moving, but there's still forces involved because of gravity. And that's the type of things that we can look at in statics. So what we can do is we can actually look at things like support cables and wires and stuff like that. So we look at like support cables, wires, ropes, anything like that type of thing. So we can look at these different types like support structures, which basically they basically hold up things. We hold up against gravity, and that's basically what we can do. So we're basically looking at gravitational force and then translating it to these things that are actually working against gravity. And that's the basic idea for what we do statics. Now, we can't do really complicated stuff like bridges and all that kind of crazy stuff because there's lots of stuff in there, but we can look at some really simple scenarios. So if we start sort of connecting this to what you guys have looked at already, I mean, like here, suppose we've got a mass, and here, let's draw like a little rope or something like that. Okay, so you got a little rope hanging around like a rock or something like that. Whatever, something like that. A little shading, okay. Now, what you guys have done before, I mean, you guys can actually, easily calculate the force of gravity. Of course, the force of gravity is pulling down on it. And of course, the rope then pulls up. And of course, this is where you get your tension from. And of course, your tension exists because of the force of gravity. And that right there, that is statics right there. The tension in the rope is equal to the force of gravity because it's trying to cancel it out so it doesn't move. Now, what you guys have done before is, if you take the rock, if you would accelerate it upwards or if you would accelerate it downwards, you get different tension. So, this would cause more tension. This would cause less tension. But this is a little bit different. We're not really worried about this type of stuff because this type of stuff, that's not statics, because we don't want any extra acceleration. We just want equilibrium. We just want this thing just to be sitting there. So the net force is equal to zero. And then we can look at the individual forces that are in the actual ropes and cables and chains, whatever, but it's not actually increasing or decreasing due to acceleration. So that's sort of like the little bit different compared to what you did before. The nice thing is you don't actually have to worry about the motion, and some people actually like that. All right, so let's get rid of this, and let's see if we can work with this a little bit to sort of show you how this comes together. So let's bring in a picture of my buddy Al. All right, so got a picture of Al right there. Let's try that. And we're going to put like a rope or something like that. So maybe it's hanging something like this. So hanging like a picture. All right, there we go. So if I ask, let's say, well, let's just make this simple. Let's say this is a 6 kilogram picture. That's a pretty heavy picture. If we found the force of gravity, which would just be mg, of course, we're looking around 60 newtons. We'll just say 60 newtons to make things nice and simple. Now, if I asked you what the tension was, if we looked for the tension in the rope, of course, that would be equal to 60 newtons. We've got 60 newtons trying to pull down, therefore we need 60 newtons pulling up. So the tension would just be 60 newtons. It's just that simple. Now, what if we just modified the situation here just a tiny little bit? Now, let's crack another picture. There we go. So instead of using one rope, suppose we used 2 ropes, something like this. Okay, so exact same picture, exact same everything. Well, I'm pretty sure that you guys are able to figure out if once again we've got 60 newtons pulling down, we are going to have 30 newtons of tension on that one and 30 newtons of tension on that one, pulling up, of course, to cancel out gravity. So it just splits evenly like that. Okay, so it's a pretty straightforward idea. Now, what if we adjust this a little bit again? Bring another L. Hey, L. All right, now what if instead, and this gets a little bit different, what if instead we incorporate some angles? It's really common for pictures and signs to be hung up with cables and stuff like that, or ropes at angles. Well, this one gets a little bit different, but we can piece it together as well. So once again, we still have the 60 newtons going down. Now, since we've got 60 newtons going down, we have to have 60 newtons going up, and we'll say the ropes are nice and symmetrical and everything, same angle, same length, everything's the same. Well, it's going to get split. The tensions are going to be split between the two, and since everything's symmetrical, they are going to be equal. But the thing is, the tension in the ropes is not going to be 30 and 30. Like the tension in this one is not 30 and the tension in that one is not 30. That doesn't work anymore because those tensions are pulling at angles. If you have 60 newtons going down, you have to have 60 newtons going up, just like in the first two scenarios. Well, these cables or ropes, whatever they are, they're not just pulling up, they're pulling at angles. But that doesn't mean that the up components don't exist. So they're not only pulling up, but they're also pulling sideways. But if that up part would still be 30 here, and that would still be 30 there. We still 30 newtons going up. But we introduce a horizontal tension as well. And those two put together would give the overall tension in the actual rope. So the overall tension in the rope will actually be higher than 30 because it's a combination of the 30 that's going up plus what you've introduced going sideways. So it's all symmetrical still, which is kind of nice. It makes things a little bit easier. It doesn't have to be symmetrical, but that's how it gets a little bit different when you start incorporating some angles. So let's just sort of expand out that third picture here a little bit. We'll make it a little bigger, and so we get a little more detail of sort of what's going on. So I'm just going to sort of redraw that third picture over here, and I need some things in here. Put some ropes on here. I'll make them a little bigger so you got a little more room to work with. Again, we're just making it nice and symmetrical. Ooh, move that over a little bit, something like that. There we go. Okay, and we'll see the little ropes or cable things. Or 25, we'll say 25 degrees, 25 degrees, 25 degrees, something like that. Okay, and we'll still use the same values as before. So our picture is still going to be 60 newtons. So once again, we've got a 60 Newton of force of gravity pulling down on the picture, which means we have to have 60 going up. And since everything is nice and symmetrical, this rope here is pulling up and this rope here is pulling up. This one will be pulling with 30 newtons, and this one will be pulling with 30 newtons. Now, those two are only equal because everything is nice and symmetrical. If it wasn't symmetrical, those two wouldn't have to be equal. We'll get into that a little bit more later on. Now, this is typically referred to as, we'll call this number 1, we'll call this number 2. Rope 1, rope 2. I would call that tension 1 in the y, and I would call this tension 2 in the y. And those two vertical y tensions are created because of gravity, and so that's where they actually come from. So this one and this one, those two vertical tensions, must combine to give you the 60 because that's what creates them in the first place. So tension number 1 in the y plus tension 2 in the y has to give you the force of gravity, or the mg, whatever's hanging. Whatever's pulling down has to pull up. And in this case, they happen to be equal, but that's just because things are symmetrical. But that's not the only tension involved here. We've also got tensions going sideways. We've introduced a sideways component. We're also pulling sideways this way, and we're pulling sideways this way. There's a tension 1 in the x direction and a tension 2 in the x direction as well. We sort of introduced that. Now tension 1 in the x is pulling left because tension number 2 in the x is pulling right. They're actually fighting each other. They actually balance each other out. So those two have to be equal to each other. If they weren't equal to each other, this thing would move side to side. And those two always have to be equal to each other. One's pulling left because the other one's pulling right. They're fighting against each other. So those two are equal. So the vertical ones add up to gravity because that's where it came from. And the horizontal ones have to be equal to each other. Now basically we've just created a right triangle. It's just a right triangle. That's all it is. And if we use basic trig, we can actually figure out the different quantities. So if we used tan theta, because we have the different parts, got the right triangle, we can use that 25 degrees. Some people actually write the angles up there a lot of the time. It doesn't really matter. It's all the same triangle. If we use basic tan theta, we could actually find out what that tension in the x direction is. So we got the 25 degrees. The opposite is 30. We can use tan theta to find out what tension in the x direction must be. So if I just sort of punch out with my basic trig, that ends up being like, well, I'll just round off, like 64 newtons. So this guy right here, I'll change the color a little bit. This is 64 newtons. Well, if that one's pulling with 64 to the right, this one has to pull with 64 to the left. Okay, and the x's always have to be equal to each other. And then what we could do is, again, it's just a triangle. That's all it is. We've got, I'll change color. We've got 64 on the bottom. We've got 30 on the side. It's just a right triangle. So if we use Pythagoras with that, we can actually figure out what the tension across the rope must be. So we've got the 64 squared plus 30 squared, add them up and root it. And it's just here, I'll just sort of like sketch it out. We just got a right triangle with our tensions. We got 64 across the bottom. We've got 30 here. That's 25 degrees. So just using basic Pythagoras, I've just basic punched out here. This is around 71 newtons. So the actual tension in the cable is 71 newtons. So this one would be 71, and since it's symmetrical, this would also be 71. Now they're not always going to be symmetrical, but these ones are. But that's basically it right there. So the tension in the cable is actually way higher by increasing or including an angle than just hanging it straight down. So the actual angle can make a pretty big difference in terms of the actual tension of these cables and ropes and that type of stuff. But that's the basic idea behind how this type of stuff works, especially like hanging sign stuff. It's relatively straightforward. Okay, the two vertical ones need to add up to gravity, and the two horizontal ones have to cancel out because it's not moving side to side. Now it's really important, don't confuse the lengths, especially when we're not going to have like the same angle on both sides. Don't confuse the lengths of the ropes or the chains or whatever we're using with the forces. It doesn't really quite work that way. It's all about the forces and stuff like that. Okay, but that's basically it. Verticals need to add up to gravity because that's what creates them, and the x components have to be equal. So really, it's calculating mg, which you've done lots before, and then it's just basic vector analysis, taking the vectors, breaking them apart, and some little triangle math, and that's it. And that's the basic idea behind hanging a picture or a sign using a couple ropes or strings or whatever you want.